Good morning, everyone. Am I audible? Hello? 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 Am I audible? Khushbu? Hello, Khushbu? Hello?
Good morning,
Please
sir.
tell me. Good morning. Am I audible?
Yes, sir.
Yes, sir.
Why are you not talking then? Please speak now. Okay, shall I begin?
Yes, sir.
So yesterday we left at this place, Banach Theorem, symbolized Banach Theorem, where X is a complex vector space and P was a sublinear function P from X to R. It's sublinear function. I am not saying it is functional, it's function, correct? Which satisfies these two properties. If Z is a subspace of X and F is a functional on Z, such that mod of fx is less than equal to px for all x in Z, then there exists by Hahn-Banach theorem says that there exists an extension of f on whole of x such that this happens. The same inequality will hold for all x in x. We will use this theorem to prove and a more general Hahn-Banach theorem for norm dispersion. Okay. Now Hahn-Banach theorem for norm dispersion. So I write this statement first. So what does it say? It says we have a norm space X, and we have a subspace of this non-linear space, and we have a bounded linear functional on the subspace say Z. Okay. Then Hahn-Banach theorem says that there exists an extension of given bounded linear functional on whole of X, and fact that extension will preserve the norm. Write it first. Bounded linear functional subspace Z of X, where X is norm space. X is space. Then there exists a bounded linear functional delta X is an extension of F. And theta has the same norm as Fh. So here, by definition, you all know what this is. This is supremum x. And similarly, x is that one mod of x. So we will prove this theorem. Let's begin to prove. So somehow we will use this Hahn and Banach theorem in order to prove Hahn Banach theorem for norm displacement. So if you see the statement of generalized Hahn Banach theorem, here we have a vector space. Okay, norm displaces are vector space. Then there is a sublinear function. So to use the generalized Hahn Banach theorem, we need a sublinear function. So first here I have to find a suitable sublinear function. Okay, so let's do that. Okay, so let's begin. So the simplest subspace of X is Z is 0. If Z is 0, then F is 0 and F theta is also 0. And then F is 0, theta to be right. This is an extension. So there is nothing to prove. So assume Z non-zero. And now what we do, we want to use generalized Hahn Banach theorem. So we will find sublinear P. You know we are using norm of F, so you know the relation mod of Fx less than equal to norm F, norm X. Correct? You know this relation. And since F is defined on Z, F is defined on Z, so this is true from Z. Okay, and so we are taking norm over Z. Right. So taking Q from here, so see in the generalized theorem, in the generalized and Banach theorem, mod of Fx is less than equal to Px. So we have to find Px. So from here you may guess what that P should be. Okay. So mod of Fx less than equal to something, that it should be Px. So we will define P. Taking a Q from here, we define P on X, define P on X, okay, by X equal to norm F, norm X. Correct? Define this. So clearly P is sublinear. You all know these norms are sublinear. Okay. So how do you see the px plus y equal to norm f x plus y? But you know this part is less than norm x plus y. So from this you will get this is the this thing x plus norm y. But this is nothing but the sorry plus norm f y. So which is px plus py. So this implies px plus y is less than equal to px py. And similarly p of alpha x and z alpha x. But you all know alpha x is mod alpha norm x. Mod alpha px. So therefore p is sublinear. And and from this we have mod of fx less than equal to px for all x in z. Now you generalize the Hahn-Banach theorem. So from light theorem, here exists f tilde from x to k such that f tilde when we restrict it to z will get f and f tilde x mod less than equal to px. Correct? Okay. So here what we get this part. So f tilde x, but you know px is nothing but mod f x and x belongs to x. Okay. But it's, so you all know what is norm of f tilde. Norm of f tilde is by definition it is supremum over all x in x, norm of f tilde x. So take supremum in this inequality, supremum over all x, when x norm x is equal to 1, taking supremum over x in x, norm x equal to 1, but we obtain, so take supremum over x 1 x is less than equal to, so supremum x in x 1, so this is fixed quantity and this part is 1 because we are taking norm x equal to 1. So this right side is norm fj. And this is the definition of norm f tilde x. So we get this equality. Oh, we get this inequality. So this is less than equal to. Okay, so far we have seen this, but you know, under extension the norm cannot decrease. So we also have f tilde x greater than f that implies tilde norm of f tilde. So this part is because under extension the norm cannot decrease. So because this is the Hahn-Banach theorem for non-linear spaces, and we have just proven it. But for proving this theorem, what we need is the generalized Hahn-Banach theorem. So I gave this an exercise. Please see your textbook and see a proof of this, understand that, and then try to understand. Feel any difficulty, face any difficulty, please let me know, and we will discuss. Correct? Any doubt?
Then
Okay. So, what next? So, next is the theorem.
sir.
Next theorem. What does it say? Says that. So, so it gives the says that there are plenty of linear function, bounded linear functional on a norm space. Okay. Does it say this? Let's see. Let's see the statement first. We have X, a norm linear space. And that X naught non-zero. Be any element in X, any vector in X, then this theorem says that there exists linear functional, bounded linear functional. Functional X that norm of f tilde is 1, of f tilde at x naught is norm x naught. So this means there are plenty of bounded linear functionals. So for each vector x naught, each non-zero vector x naught, you you can construct a bounded linear functional such that f tilde at x naught is norm of x naught and norm of that bounded linear functional is 1. So let's see how. Okay, so here this x naught is non-zero. So consider the subspace spanned by x naught. Spanned by x naught and call it Z. How do you write this span x naught? All those x in x such that x equal to some scalar multiple of x naught. Okay. Okay. This is a subspace spanned by x naught. Consider this. Okay, and now define it on Z. Define as Z. How do we define this? So any element of Z is of the form alpha x naught. So write fx is alpha. You can write x as alpha x naught, where alpha comes from k, and define it as okay. Okay, so from this, let's see what is fx then. Fx is f alpha x naught, which is mod alpha norm x naught, but you know this is nothing but norm alpha x naught. Correct? And which is alpha x naught is x. This is norm x. So from here, what we get that mod of fx equal to norm of x, like that is bounded. Is bounded, and in fact norm of f is 1. Correct? Is there any problem? Any doubt? Hello? Am I audible?
Sir.
Yes, sir.
Yes, sir.
Is there any doubt so far?
सर कल का लेक्चर आपने पोस्ट नहीं किया सर?
क्या? कल का लेक्चर?
सर कल का जो आप ऑडियो बना के भेजते हैं
हाँ,
वो आपने पोस्ट
कर दिया ना मैंने आपको फोल्डर लिंक दिया हुआ है, वो फोल्डर में ऐड कर दिया।
ओके सर ओके
मैंने एक फोल्डर का लिंक आप लोगों को भेजा है,
यस सर
वो फोल्डर में मैं डाल दिया करूँगा।
ओके
बार बार वीडियो का लिंक
ओके सर ठीक है
एक बार मैं चेक कर देता हूँ। हाँ, डाल दिया मैंने। So is this okay? So far it is okay? Okay.
यस सर
Don't say anything. I take it is okay. So far what we did. So we found a linear functional on a subspace spanned by x naught with with desired property. So we wanted a functional with norm 1 and it takes value at x0 as norm x0. Okay? Correct? But okay, so now you use Hahn-Banach theorem. Get an extension f tilde of f to x. So this means there exists f tilde from x to k such that when we restrict f tilde, that we will get f. And one more thing, f tilde x equal to z. But you know what is norm f z? This is 1. Okay. And by definition of f, by definition of this part, f tilde at x naught, then by f of x naught. X naught is nothing but norm x naught. Correct? So we prove this. So this is very important theorem. It gives you plenty of bounded linear functions. The next is corollary. So next corollary says that from space K and we have one and x2 vectors in it. There exists a bounded linear functional such that dx not equal to dx2. So what does it say? It says that the dual space separates points of x. Okay, so how do we do this? Very easy. We will use above theorem. So observe that x1 not equal to x2 implies x1 minus x2 is non-zero. Correct? From above theorem, this theorem, you have it says there exists a bounded with these properties. So this means for this non-zero vector, there exists a g from x to k such that two things happen. Now g is 1, g at this point norm x1 minus x2. Correct? Is it okay?
Yes, sir.
You know, since this is non-zero, x1 minus x2 is non-zero, norm of this is non-zero. By properties of norm. And g is linear functional. Dx1 minus x2 is minus dx2. Non-zero. This implies dx1 dx2. Correct? So We have a non-linear space. And if fx equal to 0, or f in the dual space of x, when x equal to 0. So how do we do this? So assume on contrarily that x is non-zero. Assume x is non-zero. Correct? Then from our theorem, so this corollary,
There exists
we
a
will get
bounded linear function.
here exists a g such that gx1 is non-zero. Correct? In this, then here exists a g in x dash in t linear functional such that gx is non-zero. But this is a contradiction to the hypothesis of corollary. It says that fx is 0 for all f in x dash. So we are getting a function x dash and a member of x dash such that for which x is non-zero. So this contradicts this part. Okay. Now, says for every x in a normed space, have x equal to, so it gives you a formula for norm x. Supremum over all f. In x dash is the dual space norm f. So I am dividing by norm f, so 0 norm. Because otherwise I cannot define this quotient. Okay, so let's see a proof. So we will use the theorem, this one, that for every non-zero vector, we can find a bounded linear functional such that norm of f is 1 and mod of and f theta is not equal. Okay, we will. So for non-zero x functional theta such that f theta x equal to norm x and f theta is 1. Okay. So consider this part, supremum f in x dash 1 from f is non-zero. X bar norm f. This is in fact, since we are taking supremum over such quotient, so clearly this is greater than norm f tilde. But you know norm f tilde is 1 and f tilde x is norm x. This is correct? And now use this inequality. Okay, simplify x by norm non-zero, this is less than equal to, and use inequality here.
Oh,
So
sorry.
this was x dot f non-zero dot fx by norm f. So hence the inequality. Okay, any doubt so far?
No, sir.
Next theorem. So before going to next theorem, so let's define a concept called supporting hyperplane. Okay. So supporting hyperplane means it's kind of this. So let's see via a figure. So suppose we are in R2, okay, and we have a convex subset of R2, say this ball. Then a supporting hyperplane is a hyperplane of this form. So then this line represents a supporting hyperplane. Okay, I told you that any linear subspace passing through origin in R2 is a hyperplane, correct? In R2, a one-dimensional subspace is called. So, so this is a fine hyperplane, and since support, it is called supporting hyperplane for this convex subset. Okay, let's see a proper definition. Let X be a non-linear space and suppose we have a non-zero functional, bounded linear functional, then this set, which set all x in x, okay. So this set is called suppose of this sphere x less than equal to r. So here what we are doing, so again we are in R2, say we are in R2, okay, and say we have Suppose this is the sphere of radius r. So we are taking, okay, then this set all those x such that fx, so this will look like something like this, or like this. Okay, one of these two, it will look like this. So this set is the hyperplane. Okay, this part is the hyperplane. Okay, let's see proof of this. Okay. So this is support of sphere. So let's see a theorem.
सर
which is geometry. बोले
सर
Hello?
आपने ये लेक्चर नोट्स कल सेंड किए हैं
कौन से वाले
सर यही जो आप अभी बता रहे हैं
हाँ ये मैं आज भेजूंगा
ओके सर
Okay, so this is the geometric interpretation for Hahn-Banach theorem. What does it say? It says that x be from this space okay, and x not be any point surface of this sphere. This means norm of x naught equal to r. Okay. Then there exists a plane sphere at the point x naught. So in above figure, if x naught is this point, if this is the point x naught, then we will get this hyperplane. Okay. If x naught is this point, say this is y naught. For this point y naught, we will get this hyperplane as a supporting hyperplane at y naught. Do you understand this thing?
No, sir.
And it is true for any convex region. Okay. So here this sphere is very special convection, but this theorem is true for any convex subset. Okay, let's see a proof of this. Since this norm x naught equal to r, okay, and you take r is positive, so clearly x naught is non-zero. X naught is non-zero. This means by above theorem, there exists an f, say f naught, x dash, it's a bounded linear functional such that two things happen, f naught, x naught is norm of x naught, and f naught norm is 1. This is what we will get, okay? So from this, what we get, let's see this set H, all x in x, such that f naught x equal to R norm f naught. Okay. So you know R f naught is nothing but f norm of f naught is
1.
this set is nothing but all those x in x such that f naught R.
Boundary points.
Okay. So you have already seen such set. See what this set is. This set is f naught inverse R. Correct. So this is of codimension 1, and in fact, what this set is wait a minute, what this set will be. So let's see how does this look like. So here this is your sphere. Here is point x naught. Okay. And so this h is nothing but this. This side. So you have already seen this h is a closed hyperplane. This is closed plane, and it passes through. And from the definition, from this definition, so this is a supporting hyperplane. Okay. In fact, H is closed up and it's says correct? Any doubt? Hello? Hello? And one more thing, since we have f naught x naught equal to norm x naught, okay, since f naught x naught equal to norm x naught and this is R, so it follows that this hyperplane passes through x naught. Hyperplane H passes through the point x naught. Okay, so this is an exercise in your book, textbook. Okay, so I'll stop here for today. So we shall meet on Friday. Okay. You may drop your attendance. Any question? Any question?
सर जो हाइपरप्लेन समझाया था आपने कोड हाइपरप्लेन ज्योमेट्रिकल रिप्रेजेंटेशन एक बार और
इसके ये वाला पार्ट
सर ये तो डेफिनेशन से पहले हम हाइपरप्लेन ही डिस्कस कर रहे थे
पहले हम क्या बोल आपकी आवाज
ओके
सर हाइपरप्लेन क्या होता है इसको समझा दीजिए एक बार फिर से।
हाइपरप्लेन क्या होता है ये देखो ये हमने पहले इस बारे में बात करी है हाइपरप्लेन के लिए आपको याद है हाइपरप्लेन is a subspace hyperplane here subspace a proper linear subspace. Okay, proper linear subspace of maximal dimension. Correct. So dimension of x is n.
dimension of n minus 1
A subspace y x dimension n minus 1 is a hyperplane. Correct. If you remember, we have shown that f is a linear function or f x this set that f x is 0 a hyperplane. Do you remember this? We have proven this part. We have also proven one theorem, one result that if f is a linear functional, okay, then all those x in x such that fx equal to x naught, not x naught exactly, say some alpha naught. Okay, it is an affine hyperplane. Do you remember this?
Yes, sir.
So for this, what we did, so since say this alpha naught is non-zero, there must exist some x naught in x such that f of x naught is alpha naught. You know how do we find? So from here, this fx minus alpha naught will be fx equal to alpha naught. This is fx minus alpha naught is 0. This is fx minus f of x naught equal to 0. F is linear. This will be. Let's say this is suppose this is h. H is nothing but h equal to x naught plus null space. What is null space? Null space in x such that this was a hyperplane. This x is a translate. So if you see here, this is of same form. You see this? Here, this h is all those points of x such that f naught x equal to r, but you know f naught at x naught equal to r. So this hyperplane passes through x naught. So do you see a resemblance? दिख रहा है ना आपस में सेम दिख रहे दोनों
Yes, sir.
hello so hyperplane is here hyperplane is a null space of a linear functional right
Yes, sir.
okay then any doubt any other doubt
No, sir.
okay then on Friday